This tutorial is brought to you by PE Prep Engine. Free study guides and practice questions at peprepengine.com.
Week 2, Lesson 8, Impulse Momentum and Water Hammer. We'll compute anchor forces on pipe bends, jet thrust, and deflector reactions, then turn the same momentum theorem on its side to predict the Joukowsky pressure surge from a closing valve. Bernoulli and Darcy-Weisbach both track energy per unit weight along a streamline. Neither can give you the force on a pipe bend, the thrust of a nozzle, or the reaction holding a turbine blade. For forces, you apply the linear momentum theorem to a control volume, the missing third pillar after statics and energy. Get the steady state tool, and water hammer follows as the same principle applied in time. The linear momentum theorem: steady flow, one inlet and one outlet. The sum of external forces equals mass flow rate times the change in velocity, outlet minus inlet, or ρQ times the velocity difference. It's a vector equation. Write one component at a time, x and y, with proper signs. Three contributors appear: pressure times area at each face, the weight of fluid in the control volume, and the anchor reaction. Before you write a single equation, draw the control volume. Bound the fluid with a dashed boundary. Mark the inlet and outlet faces with velocity arrows. Attach pressure labels: P1A1 pushing inward at the inlet, P2A2 at the outlet, and draw the unknown reaction R sub x, R sub y on the wetted surface. Most exam day momentum errors trace to a missing or ambiguous control volume. 4 signatures send you straight to momentum. 1. Force on a pipe bend or fitting, anchor reaction asked. 2. Jet propulsion or nozzle thrust, exit velocity changing. 3. A deflector or blade redirecting a jet, stationary or moving. 4. Sudden valve closure with a transient pressure spike, water hammer. If the question asks for a force, thrust, or pressure spike, momentum is your tool, not Bernoulli. The variable table for every impulse momentum problem: density, volumetric flow, inlet and outlet diameters, areas, velocities by continuity, mass flow as ρQ, the gauge pressures at each face. Convert PSI to pounds per square foot by multiplying by 144. Pressure times area at each face, the momentum flux term, ρQ delta V, and the x and y components of the anchor reaction. The resultant is the square root of the sum of squares. Worked problem: a 6-inch pipe carries 2 cubic feet per second of water around a 90-degree horizontal bend. Gauge pressure at both faces is 25 psi, and atmospheric acts outside, so we use gauge pressures directly. Find the magnitude of the anchor reaction. Choices 320, 560, 1050, or 1450 pounds force. Populate the table. From the diameter, the area, velocity is Q over A, about 10.2, same at both faces. For the pressure force, convert 25 psi to pounds per square foot, times 144. Then multiply by area, about 707 pounds force per face. The momentum flux term ρQV is about 40. Notice the pressure area term dominates the momentum term by roughly 18 to 1 at this pressure. Sum the components. With positive x along the inlet and negative y along the outlet, R sub x is the pressure force plus the momentum flux term, about 746 pounds force. R sub y has the same magnitude, negative. Equal magnitudes mean the resultant lies at 45 degrees. The anchor reaction bisects the 90-degree turn. Intuitively right. Resultant is root 2 times either component, about 1,055 pounds force, which rounds to choice C. Magnitude check. At 25 psi through a 6-inch pipe, several hundred pounds is the right order for a hard 90-degree turn. The lesson: at modest velocities, the pressure area term sets the magnitude. The momentum flux term is a small but non-zero correction. The same theorem covers 3 classic patterns. A free jet on a stationary plate stops the axial component, so the force is ρAV jet squared, or ρQ V jet. A deflector turning the jet through angle theta gives an x component of ρQ V jet times 1 minus cosine theta, and a y component of ρQ V jet times sine theta. A 180 vane gives the maximum factor of 2. For a moving blade like a Pelton bucket, apply momentum in a frame on the blade. the relative approach speed is V jet minus U, and peak power transfer is at U equal to half the jet speed. Switch from steady flow to a transient. When a valve closes quickly, the upstream column must decelerate fast, and its momentum converts to a pressure spike that travels back as a compression wave. Water hammer. The Joukowsky equation gives the rise. Delta P equals rho times wave speed A times the change in flow velocity. For water and steel, wave speed is around 4,000 feet per second. Stop a 10-foot per second flow instantaneously, and the spike is well over 500 psi, on top of the running pressure. The pipe period 2L over A is the decision point. Faster, full spike; slower, the reflected wave bounds the peak. Wave speed depends on both fluid and pipe. In a rigid pipe, A is the acoustic speed in the fluid, about 4,700 feet per second for water. A real pipe stretches under pressure, reducing wave speed. Thin-walled plastic can drop A below 3,000, directly reducing the spike. Slow closure rule. If closure time exceeds the pulp period, 2L over A, the peak scales down by the ratio of pipe period to closure time. 3 field mitigations. Extend the closure time, install short flexible hose sections, or add a surge tank or accumulator. 5 errors that cost points. 1. Use gauge pressure in the PA term when atmospheric acts outside. Absolute pressure double counts the atmosphere. 2. Don't drop the pressure force at the faces. The momentum flux term alone isn't the full anchor force, and at line pressures, it's the smaller piece. 3. For a bend that redirects flow, always write X and Y components. 4. On a moving blade, use velocity relative to the blade, not absolute jet speed. 5. Joukowsky applies only to rapid closure. Compare closure time to 2L over a first. And trap 0. Draw the control volume first, every time. 5 takeaways. 1. Linear momentum sums to mass flow times velocity difference as a vector. 2. Anchor force on a bend is pressure times area at each face plus the momentum flux term. Pressure usually dominates. 3. Jet on a stationary plate is rho Q V jet. A deflector through angle theta adds a 1 minus cosine theta factor. 4. Moving blade analysis uses relative velocity, peak power at half the jet speed. 5. Water hammer follows Joukowsky for rapid closure. The pipe period 2L over A bounds the spike for slow closure. Onward to Lesson 9, Drag and Viscous Flow.
The full study guide, with every equation and common exam trap, is free at peprepengine.com. Link in the description. Machine design, HVAC, structural, civil, and electrical series are coming soon. Subscribe so you don't miss them.